I'm pretty sure, but let me just check. Yep, owl.
One time, what we found was
I might have to change the video, I guess, to the owl. Oh, here we go. Yeah, it auto picked up the audio, but not the owl. So okay, there we go.
perfect. And then this.
Great.
atomic molecules, I bet.
How did you know? I think I should be, sorry. Oh, yes. Yeah, there we go. That better? All right. Is my microphone on? How about now? There's a green light now. All right, thank you. Thanks to everyone for coming. Thanks to the organizers for inviting me. I'll tell you about some of the things we've been doing at Caltech, focusing on molecules with deformed nuclei. I will skip over a lot of the background and motivation since I'm following up Eric's talk. But quick one slide summary. Molecules, because they contain very large electromagnetic fields, they amplify CP violating electromagnetic moments in electrons, but also in nuclei. And because molecules compared to atoms are around 1,000 times more polarizable, you get an effective enhancement of about a factor of 1,000 compared for molecules versus atoms. Electron EDMs are already probing, roughly 50 TeV. So that's, they've increased by 10 TeV since Eric's talk, because he said about 40. So it's, squiggly line. It's pretty high energy scales. Both the ACME and GILA EDM experiments are probing roughly this energy scale for new CP violating physics. And as you heard, and as you'll mostly again hear about, hopefully, there are a lot of advances coming. So I think it's reasonable to expect that these improvements will keep going through many different approaches, just some of which you'll hear about from me, and some of which you heard about from Eric, some of which you'll hear about tomorrow from other people. Eric mostly talked about the electron. I'll say a little bit more about the nucleus. Nuclear symmetry violations can be further enhanced by nuclear properties. So this is in addition to this molecular enhancement you get from the larger polarizability. Certain nuclei have further enhancements of their CP violating electromagnetic moments. And this gives you access to different physics than the electron EDM physics that shows up in the nucleus, things like nucleon or quark EDM, the strong force, nuclear forces. And it turns out that these effects tend to be further enhanced in deformed nuclei. There are two effects that I'll talk about. One is a magnetic quadrupole moment, or MQM, which is enhanced in nuclei with a quadrupole shape, which you heard about in thorium, and also nuclear shift moments, which are enhanced in nuclei with a shape you also heard about earlier briefly, with this same graphic octopole deformed nuclei. The way these show up in molecules is essentially identical to the electron EDM. The way that you do the measurements is almost exactly the same. So people usually just call all these like EDM experiments, even though these things are technically not EDMs. Close enough. So you can double dip on these enhancements. From the electron EDM, you get this factor of 1,000 molecule enhancement. You get essentially the same thing for, say, like an MQM, but now you can get maybe a factor of an order of magnitude or so for a sufficiently quadrupolar deformed nucleus. And for a nuclear shift moment, this enhancement is up to 1,000, or in some cases maybe even larger. So you can get very large dramatic enhancements over atomic sensitivity with spherical nuclei, which are the current state of the art. We focus mostly on symmetry violation using linear triatomic molecules. So we don't use diatomic molecules, we use triatomic molecules, and are looking towards even more complicated molecules for some reasons that I'll talk about. I won't talk about strontium OH, but you'll hear about that tomorrow. But I collaborate with John Doyle on an experiment in SROH, and he'll talk about that tomorrow. But in my group, we work with YBOH and RAOH mostly. And these different species give you access to different CP violating observables, but the idea of the experiments is very similar. We like these polyatomic molecules because they combine the CP violating sensitivity and basically the optical properties of diatomics, they're very similar. But they have a really nice feature called parity doublets, which makes them very polarizable in small fields and lets you do some tricks like internal comagnetometry, where you can operate the experiment with the molecule polarized one direction or the other to flip the sign of your science signal without changing by very much the magnetic properties. And something I'll talk about later, they have tunable dipole moments. The EDM state in these molecules is suggestively indicated by this bent state. The ground states of these molecules are actually linear. We do the experiment, the science state is a metastable bent state in the molecule with a lifetime of about 700 milliseconds. And with a doubling of about 20 megahertz, you can polarize them in about 100 volt per centimeter field. To give you an idea of what does this polyatomic structure give you, and what does it have to do with things we're interested in, here's a sort of a simple conceptual explanation of why we get parity doublets, but also what parity doublets are, if you're unfortunate enough to not know what parity doublets are, because they're great. If you have a molecule, it doesn't have to be a polyatomic, it could be a diatomic, but if you have some molecule with an orbital angular momentum, just meaning like a mechanical non-spin angular momentum, like an electron orbiting around, L, or something like a bent or nonlinear molecule rotating about its symmetry axis. When you have this mechanical angular momentum, the eigenstates in some bases at least sort of look like e to the plus or minus ij times the azimuthal angle around the symmetry axis. The physical eigenstates are not these states, but actually superpositions of these that have well-defined parity. These don't have well-defined parity. These do. They sort of look like sine and cosine in the azimuthal angle around the symmetry axis. So you get basically, two states that look like this, where this is, say, the electron wave function or the like nuclear position wave function. When you have a molecule that rotates, you get a ladder of opposite parity states. But when you have this degenerate, nominally degenerate two possible configurations in each rotational state, when the molecule rotates, the fact that these have a different moment of inertia around the rotation results in a ladder of opposite parity states. So you get a ladder of even and a ladder of odd parity states. So each rotational level in the molecule is split into a doublet of two opposite parity states that are pretty close by and therefore very polarizable. In diatomics, you can only find this when you have electronic orbital angular momentum. That's the only possible angular momentum that you can have in that direction. But with polyatomics, you always have this, either in the ground state or in excited states where the molecule is, say, bent. One of the features that this gives you, the reason we like this doubling is because you get a lot of really good control over the electromagnetic properties of the molecule. So in our case, our molecules have a doubling of about 20 megahertz. So we get sort of order unity polarization in like 100 volt per centimeter field. So that's great. If you look at, say, EDM sensitivity, which you heard from Eric, is proportional to the degree to which you can polarize the molecule. For these molecules with doublets, having fluoride plus has a doublet, by the way. You can polarize them in much smaller fields than you can in the types of diatomic, laser coolable diatomic molecules without parity doublets. For example, like YBF, you can polarize them in much smaller fields. So that's great. One thing that's not great is these types of molecules have SROH, YBOH, RAOH. They have basically a Bohr magneton of magnetic moment, which is not great. If you compare it to, say, the Gila EDM molecule or the Acme molecule, they have almost zero magnetic moment, which is a really important feature for their robustness against systematic effects. However, there's a trick that you can play with these polyatomic molecules, which is they have a really neat feature which is that they have a coupling between the spin and the internal symmetry axis along which the internal field lies. So you have, the regular old Zeeman, you have the Stark effects, but then you have this effect, which looks like the spin of the electron dotted with L, which is the orbital angular momentum of this bent molecule rotating around its symmetry axis. That you can imagine as creating a magnetic field, which is aligned along the symmetry axis of the molecule and interacts with this electron spin. That gives you a coupling between the internal axis, which has the molecular dipole, which you can tune with an electric field, and the electron spin. So for example, you can find electric field conditions where essentially this molecule is precessing around the electric field at the same rate that the electron spin is precessing around this internal axis through this coupling, and make it so that the projection of the electron spin in the lab frame vanishes. So you can make you can generically find conditions where these types of molecules are not magnetically sensitive. And I'll show some examples of that later. One of the things, so that's the platform, polyatomic molecules. So what do we want to do with them? One of the things is we want to search for a nuclear magnetic quadrupole moment. It's a CP violating moment, just like an electric dipole moment. And it can exist in nuclei as long as it has a sufficiently large nuclear spin to support a quadrupole moment, which means at least one. You can imagine this in a single particle picture as if you have, say, a nucleus with a valence nucleon. If that nucleon has an EDM and it's orbiting around, that creates a magnetic quadrupole moment. And it turns out, and then this quadrupole moment has the nucleus, interacts with the electron spin, give you CP violating energy shifts in a very similar but just kind of more complicated way than the electron EDM interacting with an internal field. A quadrupole deformation in the nucleus enhances the MQM by making it so that you don't rely on just valence nucleons. That involves inner shells. So you get an enhancement that's typically around a factor of 10 or so. And quadrupole deformed nuclei are fairly common, so that's nice. We've chosen a terbium, YBOH, to do a nuclear magnetic quadrupole moment search at Caltech. 173 YB has a nice quadrupole deformed nucleus and a large enough spin. It's a beam experiment, so you can see a photo of it here. We make the molecules here, shoot them down this beam through this magnetically shielded chamber. Here's what it looks like on the inside. See the electrodes and fluorescence collection optics. So the way we make these molecules, so the way this thing works, which you'll hear more about these in future talks, because these molecules are free radicals, we have to create them if we want them cold, we have to use, or we don't have to, but we use cryogenic buffer gas cooling. We vaporize some solid precursors with a pulsed laser in the presence of a cryogenic helium gas. So the helium gas cools the molecules, and then we can extract them out as a beam to shoot down our beam line. We optically drive chemical reactions to create the desired species. So for example, we want YBOH. So we take ytterbium atoms, which we make lots of in the ablation. We excite it to metastable triplet state, which has enough energy to overcome reaction barriers to create YBOH. For example, YB and water in their ground states won't react, but YB in an excited triplet state will. So this generally gives us about sort of 10 times more molecules. And in these cryogenic sources, this has now been implemented in lots of different alkaline earth atoms. I think in our group, we've done it in barium, ytterbium, and radium. And in John Doyle's group, they've done it in calcium and strontium. And so we can use, we are currently using this beam as is. This is also the starting point for further cooling, say like laser cooling and trapping, which you'll hear about tomorrow. So we want to do a spin precession experiment, like you heard about from Eric. And in our case, we've got a lot of problems. One of the problems is that, okay, what do you usually do? You want to make a superposition of, say, two states with opposite EDM shifts or MQM shifts and watch them interfere. In our case, M is really large, like just because we have lots of angular momentum. We've got the ytterbium spin, electron spin, this bending angular momentum. and the hydrogen has a spin, so like the spins are really large. So making these for most pairs of states, this is just really hard to do. It's not impossible, but it's hard to do. It's especially hard to do in a beam with velocity dispersion and a large volume. So if you try to think of like a coherent sort of reversible way to make this superposition, it's really hard when you factor in these problems. If you want to like, okay, use an irreversible process. That should hopefully kind of bypass these issues. If you use an irreversible process, one problem that you run into is that there's unresolved excited state hyperfine structure. So for example, if you want to do what Acme does and just say, okay, fine, like pick some states with small m's, you could do something like this. This excited state has unresolved hyperfine. So if you try to make a superposition of these with, say, coherent population trapping, these two dark states will interfere and cancel out, and you won't end up with any state at all. Instead, the solution is just like, don't do this. We don't do this. We don't make superpositions of plus and minus m. You can make superpositions of any m you want. That plus probably shouldn't be there. Just like, m and m prime. They don't have to be time reversal pairs of each other. Say, and if you choose two m's that differ by no more than 2, you can connect them with a 2-photon transition. For example, you can do like this state and this state, or this state and this state. And that works fine. You can do that. It's, like a 2-photon transition. You can see Ramsey fringes and all that stuff. But there's a big problem, which is that these two states have a first order differential Stark and Zeeman shift. And so that's like the worst thing that you could have for like an EDM experiment. So what you can do is you can do this trick I alluded to earlier. You can find electric fields conditions where you are very insensitive to fields. So you can find electric fields where the Stark and Zeeman shifts are simultaneously below 0.1% of their full value. You can also find values where either one vanishes. But the EDM shifts are still, at least a third of their maximum value. And they're static shifts. So you can still use sort of traditional spin precession methods. Just make a superposition, let them process, read them out. These exist fairly generically in polyatomics, and they typically have fields around 100 volts per centimeter or so where you get these conditions. So this is a prediction of one of these conditions in YVOH 153 YVOH around 65. Here's some preliminary data in 154 YVOH, which is much simpler to work with and understand, showing some field insensitivity around 12.5 volts per centimeter. So that's the approach that we want to take for this MQM experiment, which we're working on at Caltech. Another thing which we did recently in collaboration with John's group was a sort of proto-EDM experiment with trapped ultra-cold CaOH at Harvard, where CaOH is too light to have good EDM sensitivity, but it has the exact same structure as heavier species, which have much better EDM sensitivity. And so it's a good pathfinder experiment to test the methods. And so in this experiment, we demonstrated basically an ultra-cold EDM measurement protocol, including like all of the steps you would need, and basically did an EDM experiment and something without EDM sensitivity. But SROH and ROH are underway. Those are the things that we would like to do these experiments and eventually. So despite the fact that CaOH is a very complicated molecule, at Harvard, they're really good at working with it, and so they were able to populate this symmetry lowered parity doubled science state through optical pumping, do a microwave transfer to a starting state, and then another microwave transfer to make a superposition of two of plus or minus m states. CaOH doesn't have these various like problems I listed before. It has a simple structure. It's trapped, so you can just do things like microwaves to make these superpositions. So now you end up with this superposition of these two states, and you can just vary the precession time and then do the readout in reverse and see coherent oscillations between these two states, which have opposite EDM shifts. The EDM very small in this molecule, but principle, it's there. And this was, and in this experiment, we did the full, EDM protocol, spin precession and the science state polarized in a field with E and B fields and everything. And, seemed to work reasonably well. So hopefully this is like the path, one of the pathways, to adding some of the like more modern quantum technologies to at least the neutral EDM experiments. You can also do this magnetic tuning trick here, so you can just directly measure the magnetic sensitivity, say through like Zeeman shifts. You can find it does get very close to zero. And practically, it means if you do your Ramsey experiments here, where this is fairly large, you get some decoherence time, in this case from uncontrolled external fields, but just by changing the electric field over here, now the coherence time jumps up quite a bit because you're basically making it magnetically insensitive. In this experiment, up to 30 milliseconds of coherence time was observed. We project that you could do much better than a second with a quieter apparatus. This was in a stainless steel chamber with no shielding or anything, so it was actually just very messy. So we think that we could do a lot better than that. And again, this is sort of that condition where you get this kind of this weird precession coincidence where the electron spin is always perpendicular to the lab field. Moving on to a different type of effect that we're interested in, nuclear shift moments. There is a non-overlap between if you have a nucleus with some charge distribution from, say, the protons in the nucleus, but also some EDM distribution. Like if the nucleons have EDMs, there's some distribution of EDMs in the nucleus coming from electrons, coming from protons and neutrons. And those don't overlap exactly, and so you end up with some residual sort of charged shell with a dipole distribution, which we call a nuclear shift moment. You can imagine this nuclear shift moment as basically an electric field that points along the nuclear spin. And then atoms or molecules with core penetrating opposite parity atomic orbitals are mixed by this field, and so you get CP violating mixing of orbitals, which you can observe as like a permanent dipole moment in the atom or molecule. And it depends on basically the distribution of like charge, the difference in the distribution between charge and mass in a nucleus. This effect, nuclear shift moment, is enhanced in octopole deformed nuclei by a factor of typically like 100 to 1,000. So octopole deformed means it has this shape. This is radium-224, for example. And as I mentioned, this combines with molecular enhancements to give potentially very large enhancements. So large that even if you could only trap one molecule at a time with like a few seconds of coherence time, you could reach the frontiers of hadronic CP violation. And if you trapped lots of them, like more than one, this is a route to, potentially orders of magnitude of improvements and maybe even reaching the standard model values for CP violation in, my lifetime if I stop eating so many cookies. So just to say something about this, like why does this weird shape give you this cool enhancement? When you don't have symmetry violation, this kind of looks like a polar molecule. And as you all know, polar molecules actually aren't just like sitting there polarized. They rotate. This shape, this asymmetric shape would average away. They'd be in a superposition of, bump up and bump down. So it would look, it would not have like reflection asymmetry. However, if you have P violating and T violating nuclear forces, then you can get some mixing between these two states, and then you can end up with something where you do have some residual asymmetry. This connects. So then remember, this shift moment depends on the mismatch of charge and mass. And so if you have basically a big, messy, pear-shaped nucleus, this mismatch can be very large. It turns out that it depends not just on this shape, but also on the energy splitting between opposite parity levels. In other words, parity doublets. And these octopole deformed nuclei have rotation-like structure where these levels are much lower in energy, like KeVs versus MEVs. So these things both help make these octable deformed nuclei extremely sensitive to nuclear shift moments. Also, the theory is much more tractable because you only have to consider a few states when you're doing the theory. So the downside is that heavy, spinful, octupole deformed nuclei are radioactive. So that's a bummer. But also it has to be, at least if you want to do the things that I've been talking about, you have to put in a molecule that you can then do quantum control with. So things like you have to be able to synthesize and do spectroscopy and have some measurement protocol and all that. But as you'll hear, including some exciting stuff tomorrow, these pieces are coming together for actually a number of different approaches and species. For actually most of the things on this table. I like RAOH. It's got radium in it. It's triatomic. I really like triatomics. It has a laser coolable structure. It has it's kind of more diagonal than even CaOH, although it doesn't mean it will be necessarily easier to laser cool. But also it has demonstrated measurement protocols. This poly-EDM thing with CaOH, you do the exact same thing with RAOH. And take advantage of the like tunable moments and tunable decoherence. This has good sensitivity to EDMs, nuclear shift moments, and MQMs. It's got this octupole deformation. So it has really large nuclear shift moment sensitivity. But the challenge is it's radioactive. You can only get it in small quantities because it's like really radioactive. It's not like thorium-220, 232, which is like not really radioactive. It's very hazardous. It's radioactive, but also it decays into radon, which is a radioactive noble gas. So there are large theoretical uncertainties, especially on the atomic side. There's basically previous experimental work. And also, this is compounding with the fact that even just like a regular old molecule takes like years just to kind of do all the basic stuff that you need to do. But whatever, let's do it anyway. So at Caltech, we're studying so far 226 radium containing neutral molecules, future go to some shorter lived stuff. It's a tabletop apparatus. So this is it. It's our only experiment that is actually on a tabletop. All the other ones are actually on a floor. The main challenge is just quantity, obviously. We work with grams and grams of ytterbium. We work with micrograms of radium. But once this quantity problem is addressed, then we can start applying like all of the stuff that I talked about and that you'll hear John talk about tomorrow, and hopefully start doing some exciting stuff. The method that we're using is very general, and it should be applicable to many other exotic or trace species. So I think nothing about what we're doing is really specific to RAOH. If you have some radioactive molecule that you want to do spectroscopy on, let's talk. So we make we start with radium. We make ablation targets for radium. We make them in-house. We work with 10 micrograms at a time. We take either a solution of radium chloride or radium nitrate and we pipette it onto a hot surface. That's called drop casting. We test as much as we can with barium because it's not radioactive. But it turns out that this very simple procedure is really complicated by radiolysis, which is a word I learned from doing this, which is that the radioactivity actually changes the chemistry, like significantly, like 100%. Just because, radiation, like ionizing radiation takes, for example, water and just like busts it up into all sorts of stuff. And so we end up working, so the stuff that we're dropping onto this hot surface is a hot radioactive acid. And it does very unpredictable stuff. So this is what you get. These are 4 different iterations of stuff we got, and just like look at different colors. These are all nominally the same thing. And they just look really different. However, it turns out there are people who actually know how to do this stuff, like Alyssa Geyser and many others. But she came and actually helped us out to do this kind of properly. And so now the targets we make look really nice. I mean, it's still just basically a little smudge that you can basically not even see. But it's not seafoam green, but it's actually much better to work with. So then we take this radium target, we put it in a cryogenic buffer gas cell filled with helium. We have some hydroxide containing other target, usually aluminum hydroxide. We simultaneously vaporize them. We only get like a few thousand shots from this little tiny thing, so we have to be like very careful. We then, we do this trick with the metastable excitation of radium, to make RaOH. Then it's cool because it's all happening in a 4 Kelvin helium gas. And then we detect it through resonant fluorescence spectroscopy. We've also done work with RaOD just by changing that to something with a D there. Challenges remain, so we can make this molecule and we can see it, but if you want to go from this to like a precision measurement, there's still a lot of steps. But that's something that we and some others are working on. So last year, you may have seen me I may have shown this plot to you before. We started, because of the theoretical uncertainties on the line positions are very broad, it's like many nanometers. We do very broad scans with a broad laser. We find the transitions at say 40 gigahertz resolution. Then we zoom in with say 3 gigahertz resolution and start to see things that kind of look like molecular structure. Then you can zoom in even more and see kind of individual lines with like 100 megahertz Doppler limited line width. And you know, we are very proud of this. There's a, you know, if you look closely at this, there's a big problem, which is that it's just really noisy, which is, I guess, intrinsically not a problem, except I said we only got a few thousand shots, and there's like 100 shots just on this one plot. So, so we spent in the last year just mostly doing improvements on improving the radium production and reducing just background noise, and doing a lot of R&D with barium-containing molecules. So now on a single shot, we can get signal to noise on radium fluorescence of like over 100. So we get much more consistent production. We need considerably fewer averages, and we have like good normalization and like rejection of bad ablation shots. And so now we can take, you know, spectra that look more like this with considerably fewer points. This is some kind of, so what some of the spectra look like so far. We have this like kind of broad, lower resolution spectra. You can zoom in on these regions and then start taking like very high resolution spectra. We haven't done high resolution for RaOD yet, but we've done this kind of medium resolution for RaOD. So this is ongoing work. We've made a lot of improvements in the atom production, doing R&D with like different substrates, different chemical forms, different drop casting techniques. There's still a lot of room for improvement. We've been talking to people from the nuclear physics community who are much better at this sort of stuff than we are. And so now we're getting maybe 10 to the 12 or so cold atoms per shot. So we're getting enough that if you send like a resonant laser through the radium cloud, it's actually extinguished by the radium cloud, like it doesn't come back out. So that's great. And then, for example, just by say dialing the laser around to say like make sure we do this mostly for like normalization for our molecular fluorescence. And so just to like make sure we're sitting on the center of the line, we sort of, you know, dial it around and take like a quick Doppler spectrum. And just in doing that, this is already the most precise direct measurement of radium 226 singlet transition. And this is before even doing like, you know, sub-Doppler methods or anything like that. And this was also with these smaller, that was with these signals, these red ones. So maybe 100 times smaller than we have now. So that's something that would be fun to improve a little further. There are some other cool directions you could take with radioactive molecules. Here's a review if you're interested. Just 2 examples of things I think that are neat that I'd like to learn more about. Nuclear astrophysics, radioactive species made in stars give timing information about their production. So if you look at stars and you find out where spatially are different isotopes of some molecule, you can learn about where they were made in the star. You can also learn a lot about nuclear structure. This is something that Ronald Garcia Ruiz is down the road, has done a lot of work in precisely measuring electromagnetic properties, shapes, distributions. And it turns out that the limiting factor for these and many other applications is just that there's basically no spectroscopy on any of these things, except for, you know, there's radium fluoride, which Ronald has worked on, and, you know, some RaOH that we're starting to work on. But a lot of these molecules for interest in these applications are just completely unstudied. And hopefully now we can start applying these tools and studying them. So these challenging next steps to like turning this into a precision measurement, you know, we're on it. So John, Ronald, and I have teamed up with support from FRIB, and this is something that is being constructed at Harvard right now, so you can go see it with the goal of making like a radioactive molecular beamline scaling up to higher activity targets and also working with rarer isotopes like 225 radium, which has a much shorter half-life. In closing, I just want to mention one other thing that we've started working on, which is, what's one of the ways we can improve the efficiency of all these steps? It'd be great if we could use an ultra cold buffer gas instead of using helium, which is like 4K. What if it'd be great if you could use something that was like microkelvin, say like laser cooled atoms. The challenge is that the cross sections for collisions are very similar, but the densities are much lower with ultra cold atoms than like helium. So we're not the first people to think of this. It's called sympathetic cooling. But the problem, because of this challenge, people usually assume that the species are already, say, in the same trap. But if they're already in a trap, they're, at least for molecules, they're already, ultra cold. And so we've proposed using Rydberg excited atoms as like a sympathetic coolant. Rydberg excitation increases the elastic cross section by something like 10 to the 4 versus ground state, without commensurate increase in the inelastic collisions, at least according to theory. They are sub-ORS. And so even with something like 30 collisions, you could thermalize something from a few Kelvin to, to millikelvin. So this was something led by my postdoc, Chi, but also with help from our friend Hossein at 60 Garden Street. And so the idea is you could basically take, make a cryogenic buffer gas beam and then use laser cooled Rydberg excited atoms as like a sort of viscous drag to slow and stop molecules. So thanks for helping us out with that, Hossein. I'll throw this in again. I added this after Eric's talk. This is something from a white paper that we wrote, and we think that that realistically pushing this down by orders of magnitude is totally possible because there are a lot of demonstrated improvements in other areas which have not yet at all been implemented in these types of experiments. And I think in the next some number of years, you'll start seeing that and it'll be very exciting. So, we'll see you at the standard model value one day. So thanks to my group and my collaborators, and welcome any questions.
Okay, questions for Nick?
Oh, yeah, so the technical question, so when you use pure electric field, you cancel out what's dependent on the slope of the field or what's there a range? How precise in the here?
Oh, yeah, great question. So it turns out, for example, for this demonstration, the limiting factor was that the AC Stark shifts of the optical dipole trap kind of act like an electric field. And so the molecules sample some sort of finite range of effective E fields. And that tends to, so in other words, atoms, depending on where they are in the trap, have a different zero crossing. And so it sort of broadens this. And that's that's why that this isn't, greater than infinity seconds. I think this greater than seconds, several seconds coherence is basically assuming that you can cool the molecules colder in the trap. But then that they still sample some finite volume, because that will probably be more of a limitation than the actual external E field stability you can apply, especially over a very small volume. But yeah, we have some estimates in the paper. We have some estimates of, given typical values of field control that you can get, what, how effective would this be? And the actual, the DC control on the electric field would give you a coherence time long enough that you'll definitely just be limited by something else. You can also find states where this slope is opposite. So in CaOH, there's another one a few volts per centimeter away where this slope is opposite. And so realistically, you'd probably sit at both of those because they'd have opposite, G factor versus E field slopes.
Okay, one more question for Nick. Dave, well, I'm gonna start setting up Jean's computer. Okay, go for it. Go for it.
Yeah.